In this video, we will be covering the lecture over sections 4.1 through 4.3. In these sections, we're focused on a different kind of data set, a bivariate data set. So instead of having one variable that we're analyzing two variables. So one of the first graphs that we can create is called a scatter diagram. And very similar to your college algebra, you have your x-axis, which is for our explanatory variable, and our y-axis for our response variable. And when we're applying these coordinates, we can come up with different types of shapes. So the first two, these are linear relationships, and you can tell that it looks like the graph appears to be a line. So this one, our line is going up and to the right, this one is going down to the right. So if our graph is going up and to the right, we call that positively associated. And if our graph is going down and to the right, we call that negatively associated. Sometimes you can have graphs where there is a non-linear relationship. So there could be other types. Here, we will have a parabolic type, and here a cubic relationship. But in this level, we just care about whether it's linear or non-linear. And sometimes our points don't follow a particular pattern, so we say in that case there's no relation. So in order for us to definitively say what type of relationship we have, there's something called your linear correlation coefficient. And the symbol that we use for that is lowercase r to stand for our sample, rho if we had a population. And your linear correlation coefficient measures your strength and direction of a linear relationship. So just like in these two pictures, another type of relationship could exist, but the linear correlation coefficient is only for linear relationships. This value of r is always going to be between -1 and +1 inclusive. And if your value is a -1 or a +1, that is an absolutely perfect relationship. And in real life, you would never end up with that. That means that every point lies exactly on the line. If your r value is close to 0, then that means there's little or no evidence of a linear relationship. Your correlation coefficient is not resistant. Changing one value does dramatically change the result or your calculation. So here's a website where you can go and practice and confirm for yourself that when you move just one point, this will dramatically affect your linear correlation coefficient. So what you have are the scatter plots where your current correlation coefficient is 0.5. And if I take one point and just move that one point, that affects your value of r. It changes that particular value. You can also use these sliders to see what your scatter plot will look like if your r value is closer to 1, or what your scatter plot would look like if your r value is close to 0. Likewise, if it's close to -1. So in problem number 13, you have 4 different scatter plots, and your job is to identify which of these scatter plots matches the linear correlation coefficient. So the tip I've given you here is start with the graph that's most closely aligned to a line. And what you should see is that all of these graphs are going up and to the right, so all your r values are going to be positive. The one that's closest to a line is going to be graph 1. So that means it should have the highest r value. So that's going to match to D. The next thing you want to do is find the graph that is completely different from a line. It looks nothing like a line. So the graph that's closest will be number 2. So this r value is going to be closest to 0. So for number 2, this is going to be letter C. Then you need to decide, the last two we have is r of 0.787 and r of 0.523. So this graph that matches to A is going to be more closely aligned to a linear equation than the other one. So looking at 3 and 4, the one that's most closely formed to a line would be 3 and 4. And normally the issue here, a lot of students would say, well, these points seem closest, but this point is the one that's going to affect your R value the most. Remember we said that R is not resistant, meaning if you change one value, if one number is completely different, then that's going to affect your R value dramatically. So if you look on your x-axis, all the points that have the same x to this, these values are closest to the x-axis. And this one point is dramatically different. So that's going to dramatically affect your value of R. In order to definitively say, yes, there's a linear relationship or no, there's not, then we have a critical values table. And this critical values table only goes up to 20, a sample size of 20. But in your project, you have a link to a critical values table that goes up to higher than that. So the way you use this table is you find your linear correlation coefficient. You take the absolute value of that number. Then you go and look at the table and you match up the corresponding sample size. If the absolute value of your correlation coefficient is larger than this one, then we can say, yes, a linear relationship exists. So one more time, if the absolute value of the correlation coefficient is greater than this critical value, and the critical value is once again determined by your sample size, then we say, yes, a linear relationship exists. Otherwise, no linear relationship exists. A linear correlation coefficient implies that it's either strong positive or strong negative association, but we can never, ever, ever say that one variable causes the next. And here you have a link to some spurious correlation. So variables that when you plot them, the graph is very closely aligned to a line. Your R value is very close to -1 or +1. But when we look at the two variables, they are completely different. They have no relationship to one another. So in problem number 21, here we're given examples and we're asked to think about whether we think a positive relationship would exist. Positive means your graph is going to go up and to the right. A negative correlation exists. When you graph these two variables, it's going to go down and to your right, or no correlation. So looking at A, the number of children in a household under the age of 3 and expenditure on diapers. So the variable that they identify first, this is going to represent your x-axis. So as the number of children increase, so you're thinking about no children, how much would you spend on diapers? But if you had one child under 3, how much would you spend on diapers? 2 children under 3, 3 children under 3, 4 children under 3. As you're increasing these number of children, then you're going to also increase the amount that you're spending on diapers. So for A, this is going to be a positive correlation. As one variable increases, the other variable also increases. At the bottom, what you have are the steps for how to enter data into your calculator for bivariate relationships. You have an X and a Y. You have two variables. So for all students, the first thing you want to do, if you don't know whether you have an old operating system or not, is you want to go under catalog. So your catalog is right above 0. So anything that's above a button, you have to press second first. And then we want to go down to diagnostics on. Your alpha button is already selected, so you can just press a letter to jump down to D. So here's our D, and we're going to press that button, and that way it just saves us a couple of steps in arrowing down. So we want to go to diagnostic on, and we press enter, and we're going to press enter one more time to complete that step. So now what we want to do is actually enter the data into our calculator, and we're going to use this example number 26. So we have credit scores and we have the corresponding interest rate. So the way you enter data in your calculator is we're going to go to stat, and we want to go to the first option, edit. You can press 1 or you can press enter. here we want to make sure we're under L1 and L2, and we want to clear out our data set. So we're going to move our cursor all the way up to the top. Your black box should be on L1. We're going to press clear and then enter. And that removes all the data from your list. Once again, go up to the very top. Make sure your black box is around your list. Press clear, and if you press enter. If you press delete, that will delete the entire list. And the way you restore that is you would go under Stat and Setup Editor. Press enter twice, and it will restore any list that you have deleted. So now we want to enter our data, and you press enter between every line, making sure that once you're done, you go back and check your values, because it's very easy to mistype on the graphing calculator. So from here, we can create a scatter plot in our graphing calculator. Right above y equals, we have stat plot. So we press second and stat plot. We want to select the first option, so we're going to press enter. And we want to make sure our plot is on. Your black box should be around the word on. The way you toggle is just by moving your cursor over and pressing enter. Wherever your black box is, that's the current setting you're on. The type, we want the first one, and that represents our scatter plot. Once again, press enter to select it. The black box should be around it. Our X list is L1, our Y list is L2. Your mark is the point that you're going to see for actually graphing this. And then we can press graph. And you should see nothing, because the original window you have in your calculator is not set. So the easiest way to fix that is to press zoom, and option number 9 is zoom stat. So the calculator will look at your data set, and it will automatically format the window so that you can see your data set. So here's our scatter plot for our particular data. In order to find your correlation coefficient and other information, where we're going to go is we follow these steps, press stat. We want to go to the second column, calculate, and we want to select linear regression. This is what the screen looks like on a new operating system if you have that on your calculator. So your X list is L1, your Y list is L2, your frequency list we can leave blank. If you want to store the equation, you can do so. And you go down to calculate. And here are your results. And we'll talk about what these other screens mean, but R at the very bottom is your correlation coefficient. It tells you your strength and your direction. Your direction is negative because you have a negative value here. And this will be very strong because this value is close to -1. If you have the old operating system, when you go to stat, calculate, and option number 4 for linear regression, this is the screen you will see. And you do not need to type in anything else unless you put your data into a column other than L1 and L2. So when you press enter, you get the same exact results. So the other information that you're provided is the least squares regression line. This is the best line that can be created to fit the points in your particular data set. So y hat represents your least squares regression line, also known as your prediction line. Your coefficient of x is b sub 1. That is still the slope that we use from college algebra. In college algebra, we just use the letter m to represent your slope. B sub 0 is still your y-intercept, same thing as b from college algebra. The way we interpret our slope, for every 1 point increase in the x variable, you always need to interpret this based on your particular problem. The y variable will increase if your slope is positive, or decrease if your slope is negative, by the absolute value of a slope on average. And here's a tip: if your slope is negative, you do not include the negative sign in the b sub 1. It's always absolute value of that. The way we know whether it's positive or negative is if we say increase or decrease. for our particular example, remember our x variable is our credit score, our interest rate is our y. So A represents the coefficient of x, that is our slope. So the way we would interpret our slope here, say for every 1 point increase in the x, which is our credit score, then our interest rate, the y variable, is going to decrease, because it's negative, by 0.08 on average. That's our interpretation for our slope. Your interpretation of the y-intercept depends on two questions. Just like in college algebra, the way you find your y-intercept is you set x equal to 0. So in order to determine if you have a y-intercept, you have to answer both of these questions. Is 0 a reasonable value for your explanatory variable? Because the way we find our y-intercept is by setting x to 0. So if x equals 0 is not reasonable, then there is no interpretation. Our second question, do any observations in our data set, are they near x equals 0? Because once again, the way you find your y-intercept is you set x equal to 0. If you answer no to either of these questions, then that means there is no interpretation. If you do have an interpretation, it is the y-intercept is the value of the response variable, the y, when the value of the explanatory variable, the x, is equal to 0. Looking at our data set, is x equals 0 reasonable? No. FICO scores have a range of 300. There's no way you can have a credit score of 0. So there is no interpretation for this y-intercept. Because x equals 0, a credit score of 0 is not possible. The smallest value is 300. If you answered either question, there is no interpretation for the y-intercept. In section 4.3, we talk about the coefficient of determination, your r-squared value. This tells you the proportion of total variation in the response variable that is explained by the least squares regression line. How good of a job does this particular equation do in modeling your scatter plot? This value is between 0 and 1 inclusive. We use capital letter R here. If your r squared is equal to 0, that means your least squares regression line explains nothing. If your r squared is equal to 1, least squares regression line explains 100% of a variation. It explains everything that's going on in this particular problem. The closer your coefficient of determination is to 1, or 100%, the better the line describes the changes. So here are 3 different examples. If you look at data set A, you have your scatter plot, you have your least squares regression line, and this line is doing an excellent job. It's going through almost every single point. So the value of r squared is 99.99%. So our interpretation, 99.99% of the variability in y is explained by the least squares regression line. In data set C, you see your scatter plot, and this line does not do a very good job because it's not cutting through any of these points. So C, the r squared value is 9.4%. And here's our interpretation. If we look at our output from our problem, our r squared value is 0.95, and we can change that to a decimal, a percentage, by multiplying by 100%. So we would interpret this as saying 95.23% of the variability in interest rate is explained by this least squares regression line, which means this line does a very good job at predicting values. So in example 3, you have different scatter plots and you want to match them with the corresponding r squared value. And just like with your correlation coefficient, start with the easiest ones first. So this graph, your line is cutting through all of these points. So it's doing a very good job of explaining the variation, the prediction. So your R-squared value is going to be 1 here because it forms an exact line. The next easy one, you want to look at the graph and see what graph are the points scattered completely all over. So that should have the smallest R-squared value. So D should match up with graph number 1. Now we're left with graph 2 and graph 3. And what you should see is that in graph 2, your points are more closely gathered around this line, which means your R-squared value is going to be higher. So between the two choices we have left, A and B, this graph corresponds to B, and this graph corresponds to A. So we already created our scatter diagram. We believe that the credit score is the explanatory variable. Your interest rate depends on the credit score that you have. So your explanatory variable, your X variable, will be the credit score. The response variable, your result, your dependent variable, is the interest rate. Determine the linear correlation coefficient. That is symbolized by R, negative 0.98. Does a linear relation exist between the FICO score and interest rate? In order to definitively say, we have to use our critical values table. So, in our data set, we had 6 observations. Our sample size is 6. So we go and look at our critical values table. We look at a sample size of 6, and the value to beat is 0.811. So if the absolute value of our correlation coefficient is greater than the critical value, we say a linear relationship exists. Our R value is negative 0.976. We take the absolute value of that, we get 0.976. That value is larger than 0.811. So we say yes, a linear relationship does exist. Regardless of whether a linear relationship exists or not, write the equation of the least squares regression line. So from our output, we're going to round to 2 decimal places. So if we're rounding to 2 decimal places, our least squares regression line, and I will put the notation on there for the hat symbol, y hat is equal to negative 0.08x plus 61.37. To represent slope, we used M. On the graphing calculator, to represent slope, they use A. In our textbook, to represent slope, they use B sub 1. So we'll follow that notation. B sub 1 is equal to negative 0.08. And this is supposed to be a subscript. Identify the y-intercept from the least squares regression line and interpret. So our y-intercept on the calculator is B. In college algebra is B. In our textbook it is B sub 0. So when we identify the value, we just tell what the value is. Our interpretation, we have to check our requirements. So the requirements were, is there any value in our data set where the x value is close to 0? We said no. And is 0 possible? No. So no to either one of those questions. There is no interpretation. Use the model to predict the interest rate with a credit score of 545. So when we're using this equation to make predictions, we need to make sure the value is even in this range. If it's outside the range, being smaller than 545 or larger than 750, that's called extrapolation, and we do not want to use our equation for that. So here, since 545 is reasonable, we're going to take our best fit line and substitute in the value of 545 for x. And what we have is 17.77. So with a credit score of 545, according to our model, we expect that the credit score will be 17.77. Find the residual of the first observation. So our residual is our observed value minus the predicted value. So our observed value, looking at our data set, with a credit score of 545, our observed interest rate is 18.982. So your observed is whatever is already given in your data set. Your predicted is whatever the model says you should have. When we substituted in 545 into the equation and we receive that value back, that is our predicted value. So when we subtract these values, it gives you your residual. Our residual is positive. Which means that our point that we're looking at, our residual, is going to be above our line. R squared, and we normally change that to a percentage, 95.23%. Interpret the coefficient of determination and comment on the adequacy of the model. So we would say that 95.23% of the variation in the y variable, which is our interest rate, is explained by this model. And it's close to 100%, which means the model is doing a pretty good job of making interpretations. Interpreting those values. Now, Statcrunch can do the same exact thing. Whenever there are any problems in your textbook, once you're in My Stat Lab, you have the option of selecting those problems. And you do that by clicking on Statcrunch. And the first link says datasets from your textbook. So this problem is coming from, it's problem number 26 in chapter 4. We'll try section 1. Yes. So data is already in. Of course, you could open Statcrunch and type the values in as well. So we go to Stat and we go to Regression. We want simple linear. Our X variable is our credit score. Our Y variable is our interest rate. We can do hypothesis testing with these values, confidence intervals. We don't get to that until chapter 9. We can do prediction of Y. So our X value we wanted to predict was 545. We can select our residuals as well. And at the very bottom, our graph, we can create our scatter plot. So our x-axis would be our credit score. Our y-axis label would be our interest rate, and our title would be credit score versus interest rate. So when we compute, you have one or two screens available. So at the very top, here is our equation for our best fit line, our least squares regression line. So they put everything in terms of what the actual variables mean instead of using the x and y. So our dependent variable, our y, is the interest rate. Our independent variable, the x, is our credit score. We have a sample size of 6. R is our correlation coefficient. Here's our R squared value. And they also have that same information in the table as well. If you're doing hypothesis testing on the slope or y-intercept, here are your p-values. Then at the very bottom, you have your x variable and your predicted y for that particular problem. The number's a little bit off from what we calculated because we rounded on our values, and in Statcrunch they do not. On your next screen is where you see your scatter plot, and they put the best fit line superimposed on that graph as well. And on your table, graph as well. And on your table, a new column was added for your residual.